Hello and welcome to the final part of our A-star algorithm series. In the previous videos, we created a custom nav mesh system and an efficient method to get neighbors of a tile. If you haven't watched those, the links are in the description. Now, let's dive into the implementing the A-star algorithm. First, inside the generator class, create a new function to find the paths. To set it up, let's build a new struct that defines the start and target locations. I'll call it s_as_path_info. The first variable is the start coordinate. And the next one is the target location. We can optionally add a boolean to determine if diagonal movement is allowed. This is helpful if, for example, you have an air unit like a helicopter that can move diagonally or a tank that cannot. Once the struct is ready, add an input to the function and set its type to the new struct. This function can be in the pathfinding category. As outputs, we'll return a boolean to check if a path was found and another one to return the tiles in paths. And tiles must be an array. Let's break the paths. I want to check the equality of the start and target. In blueprints, there is no direct way to compare custom structs for equality unlike C++. To solve this, we'll create a function library called bpfl_general. Inside, we'll make a function to check if the coordinates are equal by comparing rows and columns, returning the result as a boolean. As inputs, we need two coordinates. And as output, we need a boolean. And we just need to compare rows and columns. And we can directly return the result of comparison. Now back in the generator class, we can use this function to compare coordinates. I can make the function pure, so there is no need for wire connections. If they are equal, we can fail the function early. Otherwise, we need a function to find the tile by its coordinates from the tiles array. I'll call the new function getTileByCoordinate. It can be categorized under the tiles and can be pure and const. As its input, we need to pass the tile's coordinate. For output, we must return a tile. Let's first check if the input coordinate is valid. I'll create another function to make sure the coordinate itself is valid. This function is under the tiles category and also it's a pure and const function. For the output, we just need a boolean. And as its input, I need a coordinate. All we need to do in this function is compare the input coordinate against the map size. The calculation is very simple. First, let's check the row if it's greater than -1. Then we need to check it against the map size, and it must be less than the map rows. Both conditions must be true. Next, we need to do the same steps for the column. It must be greater than -1 and less than the map columns. Now we can combine them into a single AND node and return the result. Back to the previous function. Let's make sure the provided coordinate is valid. If it's not, we can return the function early. Otherwise, we can go further. Instead of using a costly for loop to check coordinate against all tiles, we'll convert the coordinate into an array index using simple math. I'll multiply the tiles row coordinate with the maps columns. This will send us to the exact row where we can find the tile, and we just need to add this to the tiles column so we can move to the exact tile location. Now from our tiles array, we can get the tile with the index we just found. Before I return the tile, let's add a safety check. I want to make sure the index is less than the array length so we don't get any errors. Now we can return the tile. If the index is not valid, we can return null. Back to the findPath function. First, I'll get the start tile, and I'll store that in a local variable so we can use it later. If the start tile is not valid, we can fail the function. Next, I'll find the target tile. We can remake these nodes again. I'll promote this as a local variable too. If this tile is not valid, we can also fail the function. Next, I need to check whether the target tile is walkable or not, so we don't run the algorithm for a tile that can't walk on. We have this function from the custom navmesh video. Now we need an array to store tiles that we know about. If you remember from the intro episode, we have tiles that are not selected by the algorithm yet, but we know their cost as they are neighbors to the selected node. We also need another array to store tiles that are selected and visited by the algorithm. Let's add the start tile to the open nodes array, so the algorithm will go and check its neighbors, and if they meet conditions, it will add them to the open nodes array. I'll use a while loop node here. While is a kind of loop that runs until its condition is true. In this case, I want to run the algorithm until we have tiles in the open nodes array. We actually know about their costs, but still have not been visited by the algorithm. As the algorithm selects a tile, it will be removed from the open nodes array, so this array will be empty at some point. If we completed the loop and the path is not found, we can fail the function because there is not any more walkable tile left to check. If you remember from the intro video, we need to store some variables on each tile, so I'll create a new struct for better management. The first variable is parent. If you remember from the intro video, each tile needs to know its parent, so we can trace back to them to build up the path. The next variable is the G cost, which is the cost to travel from the starting tile to each tile. The last variable is the H cost, which is the cost to travel from each tile to the target tile. Now let's go back to the tile class and make a new variable for the new struct. I will make this variable private, so it will not be accessible from outside of this class. And I will go old-fashioned by creating setter and getter functions, so I will have more control over this variable in future. Let's go for the fcast. It can be under the pass category and also pure and const function. I didn't create a variable for that, as it's just the sum of the h and g cost. By duplicating this function, I'll create the function to get the g cost. Usually the algorithm doesn't need that, but I'll add it to make a complete set of functions. The last getter function is for the h cost, which is the algorithm used when the f costs of two tiles are equal. Now let's create setter functions. I'll start by creating a function for the g costs. It can be in the same category as others, and as input I need an integer. To set a variable inside a struct, we need to use the setMember in a struct node. While the node is selected, enable the variables you want to edit from the Details tab. Now we can duplicate the same function for the h cost. Don't forget to swap the variables in the set node. Now setter functions for the costs are completed. We can make a getter function for the parent. Getter functions are pure and const. We just need an output of type tile. And we can return the value from the info variable. And finally, we need a setter function for the parent as well. It only needs an input of type tile. I use the same method of using the setMember node to set the parent in the variable. Back to the generator class and the findPath function. On each iteration of the algorithm, we can select the first tile in the NotVisited array and store it in a variable called currentNode. Just consider each node as a tile. I'll use a sequence node to separate each part of the algorithm. What the sequence node does is just run each of its nodes when the previous node is completed. The first part of the algorithm is to loop through each node in the open nodes array to see which one has the lowest f cost compared to the current node or tile. If both f costs are equal, we can compare their h costs. If either of these conditions are met, we can replace the current node. So if the f cost is lower or the f costs are the same but the h cost is lower, we can replace the node. What this section does is help us to find the next tile we need to check. In the next step, we can remove the selected node from the open nodes list, so we don't check that again. Also, we need to add that to the closed nodes list. The next action we need to do in the algorithm is to compare the target against the selected node. If they are the same, we found the target. To make the pass, I'll create another function. As its input, I need the start and the target tiles. For its output, I need an array of tiles as the path. As always, let's make sure the start and target tiles are valid. Then I'll create another local variable to store the current node that we are checking while making the path. We need to start from the target tile, so let me replace this with the target tile. We can use a while loop node here. And its condition is comparing the current tile with the start tile. We run the loop until the current node becomes the same as the start node. I'll create an array to store the path. As we read the parent of each tile, we can add it to this array. And we need to update the current node in each iteration. And finally, when the loop is completed, we can return the result path. This function can be categorized under pathfinding. Now let's call the new function. By checking the length of the returned path, I can check whether the path is built or not. And that can be used as our function output. And we need to connect the path too. We can also add a comment for this step. If the selected tile is not the target, that leads us to the next step, which is finding the neighbors of the selected node. To check if we need to find the diagonal neighbors or not, we can use the info from the function input. For example, the unit that has requested a pass might be able to move diagonally. Please keep in mind, this is only for the square grid. You can optionally store neighbors in a local variable and iterate over that. First, we need to check if the neighbor is selected before or not. To make a cleaner graph with fewer wires, I'll promote the current neighbor from the loop into a variable. If it's selected, we have nothing to do. Otherwise, we need to check if the neighbor is walkable or not. By adding the selected node gcost to the neighbor's distance, this will give us the total G cost to the starting tile. If this neighbor has been checked before, it should have a G cost that we can compare to the new G cost. And if the new G cost is lower or the neighbor has not been checked before, we need to update the values on the neighbor. That's better to first check if the tile has not been checked before. If one of these conditions is met, we can update values on the neighbor. First, I'll update its G cost to the value we just calculated. It's the cost to move to the neighboring tile from the starting tile. Next, I'll update its H cost by just getting the distance from this neighbor to the target tile. And I need to convert that to an integer. For the last step, we can update its parent. Since we had two conditions to update these values, before adding this node to the open nodes list, I want to make sure it doesn't exist in the array. You could use other nodes like add unique to make sure the tile is not duplicated in the array. Now we are officially done with the A* algorithm. The next steps are optional. I want to create an enum to easily change the colors of tiles, whether they are selected or they are part of path. The first state is none, so the tile has the normal color. The next state is selected, and the last state is path. Now we need to update the onInteract function in the interface. We need to change the input type to the color mode we just made. Now go to the tile class and replace the select color node. And we can use the mode as the index. We can connect the colors we had before. And we need to create one new color for the path. I will change the color to yellow. I think that it would be good to separate path tiles easily. And don't forget to connect it to the path node. Now we can delete this old select color node. Also, I don't need to print the neighbors of a tile. This was for the testing we had in the previous videos. Now we need to entirely update the click function. We need to keep the selected actor when a new actor is clicked. Also, let me update its name to the start path. And I can duplicate that for the end path. If the start path is valid and also the end path is valid, we can reset both of them. If the selected actor is valid and it's the same as the start path, we can reset the start path here. Otherwise, if the new actor is not the same as the start path, we need to check if the start path is valid or not. If it's valid, we also need to check if the end path is valid or not. If it's also valid, we can update the start path as the new start path is requested. And we can select that using the onInteract function and reset the previous end path. But if the end path is not valid, I can store the clicked actor as the end path. I also need to select that by calling the onInteract function on that. To tell the generator that the start and end path is selected, I'll use an event dispatcher, so I can bind a function from the generator to this event. It's like adding a light on top of this class, and when this light is turned on, the generator class sees that and finds the path. But our light can also have extra wires to send the signal which tiles are selected. I'll set the input variable type to the same as the start and end path variables, which are actors. Now we can turn the signal on and send our start and end path. I want to add another signal to tell the generator that the start and end path actors are not selected and ask him to reset the tiles color to their normal color. I'm also about to forget to store the start path if it's not valid. Back to the generator class, and let's bind some functions to those event dispatchers we made in the player controller class. As this method is designed for single player, I can just get the first player controller in the game. By casting it to our player controller, we can have access to its functions. It can create a new function for you to bind to that event dispatcher. I'll rename the new function to a meaningful name, and we can categorize it under pathfinding. This time, instead of the validation node, I'll use the cast node, because it validates that start path and then converts it to the tile class. If both casts are successful, I can call the findPath function. Now I can build its input by reading coordinates from the start and end tiles. This is the place for the square grid. You can request a diagonal path or not. If the path has been found, I'll store it into a variable so I can reset tiles later. You may not need this if you are not going to highlight the tiles on the path. This time, instead of a for each loop, I'll use a regular loop because the target tile is in the path and I don't want to change its color, so my starting point would be 1, as the 0 is the index of the target. Now I can get the tiles from the active path and call the onInteract function on each of them, with the mode set to path. If you are going to highlight the path, we need another event to bind on. This time we have to bind to the deselect path event. This is wrong. We need to bind This time, it will show a list of functions that have the same input as the event. Let's create a function for the deselect path event. It can also be categorized under the pathfinding category. All we need to do in this function is just call the onInteract function on active path tiles and set them to the normal color. Let me call the message version of the function to the moment of truth. Let's test what we have made so far. As you can see, the path is made, but the problem is the color of the start is also changed. That's an easy fix. In the loop, we must start from the first index, but the last index is the target, so we can skip that. This time, as you can see, the problem is solved. Let's enable the diagonal movement so we can test that too. And that's also working great. Let's change the tiles to the point top hexagon to see how it works. Let me quickly adjust the camera. And there we go, it works perfectly. And for the last test, let's change the grid to the flat top hexagon. This is also working as expected. Thank you for watching this. I hope this A-star series can help you to understand the algorithm better and how to implement that in the Unreal Engine. You can join my Discord if you have any questions. Also, don't forget to check my Monday Market Day series.